policy making. Now, today we have really the privilege to have Professor Ellis from Boston University, who is part of one important network together with myself and Josef Enriquez, who's here, that it's about risk adjustment. In fact, he's been for many years, on top of being the founder of that network, which is a network that really includes the top experts and industry experts on risk adjustment globally. On top of being the founder of that particular network, which includes a number of European countries as well, he has been the country representatives for a number of years, and clearly, I would say the global authority when it comes to risk adjustment. In fact, the first time I read about Ellis was during my Ph.D. times, the Handbook of Health Economics chapter on risk adjustment with Professor Van de Ven, who was my thesis advisor. So Randall has been a great mentor to all of us working on issues that relate to health insurance, payments in particular, and risk adjustment. And today, he will speak about a novel machine learning algorithm that he has been working on for a while. So, Randy, thanks for being here, and the floor is yours.
Great, thank you. I've presented this paper a number of times, but this is a diverse international audience, and I've tried to make it accessible and not use so many American acronyms, so that's always a challenge. This is a paper that's 5 years in the making, and this is our culminating paper from this larger project. I put this in to point out that there are 4 economists, all from Boston University. There's a heavy slant towards BU in this project. And then there are also 4 physicians. And I found the best way of hiring physicians is to reward them with paper publications, since I can't pay them enough for all their time, but they spend a significant amount of time. Also, Arlene Ash is the senior person who was originated some of the hierarchical modeling that I'll be talking about today. And then I have to acknowledge the funding from the Agency for Healthcare Research and Quality in the US, and of course point out that all the opinions are my own and not anyone else's. Okay, so the setting here is that in the US and also all around the world, many different health plans and provider groups are changing their payments so that instead of paying doctors and hospitals a fee, they're working towards bundled payment so that you pay based on patient need, and you can use a variety of pieces of information for patient need. The most popular around the world is diagnostic information, and in the US and in Australia, hospitals are often paid based on diagnosis-related groups, DRGs. There's an Australian refinement, the US refinement, and many others around the globe. In addition, when there are competing health plans, as we have in the US, they're often paid a premium amount that is risk adjusted for each enrollee that's supposed to reflect the expected cost of their enrollment, not just the actual costs. And that framework is called risk adjustment, and the formulas that are used are actually risk equalization. And I'm going to be talking about modeling that we've done in support of doing careful risk adjustment. And the formula that I'm focusing on is the one that underlies the Medicare and Obamacare that are used in the US, that I'm going to be focusing on diagnostic only models. It is true that in the US and in much of Europe, there are also models that use pharmacy information that could be added on to the classification system that we developed here. And I wanted to, one of the reasons why this is exciting for me to do is that along with Arlene Ash and Gregory Pope, I was one of the developers of the architecture of the payment formulas used in these Medicare and Obamacare, and also in Netherlands and in Germany and other places. But the biggest concern is risk adjustment formulas in the US especially are not keeping up with technology. And one of the big changes in the risk adjustment world was, in the United States at least, was when they adopted this elaborate diagnostic classification system for the 10th revision of ICD-10. And basically, it increased the number of diagnostic codes from 17,000 to 74,000 codes in the US in 2015. And essentially, the problem that arises is that it makes it even easier for providers and health plans to potentially game the system, because assignment is not automatic. There's some endogeneity to diagnostic codes. And computers are getting better, and artificial intelligence is going to make it increasingly easy for these codes to be manipulated, perhaps to increase revenue, or make your patients look sicker, so other performance measures also may be easy to gain. And the government formula in the US is not keeping up. We don't update it very often, and largely the classification system has not changed since Arlene and Greg and I developed the formula in 2000, so that's a long time. Just as an example, last year, there was a huge uproar with a bunch of lobbying about Medicare fraud, where plans were upcoding the apparent severity of some of the patients, especially for diabetes and certain heart conditions. And I wanted to work through that example so you can see what the nature of the problem is. The current formula for diabetes in both the Medicare program and in Obamacare has only 3 categories of diabetes, very simple. And at the top was acute complications, and then less serious are chronic complications, and then finally patients who may have ordinary diabetes with no complications yet. And it was the case that when we developed the model, there was a hierarchy of payments for these, with a number for the acute complications about 5 times the payment of people without complications. But as there was increased upcoding, and in some ways the difference between acute and chronic is just a judgment call by the doctor. And so they already had switched those two to say, well, we're going to pay the same amount. We're not going to reward for coding the acute complications. So then it turns out that then everybody was getting upcoded from without complications to with some kind of complication. And so just this year, they simplified the program again and dumbed it down by only making one price for all diabetics. Well, you can see they're losing a lot of information when they do that, and there must be a better way to do that. And if you look at the detail of those different diagnostic codes, you can find that there's actually only 5 diagnostic codes in the US that are explicitly saying without complications. So a doctor has to go out of their way to pick a diagnosis that says, I have a diabetic type 2 and there's no complications. Otherwise, there's a long list of other codes, 400 of them, that let them choose all kinds of potential complications, including the bottom one is unspecified complications. I don't even have to say what's wrong. It's just they have diabetes with something else. Or my favorite is diabetes with periodontal disease. An awful lot of people have some gum bleeding, which would seem to qualify for putting that. And suddenly now I get the $2,000 bonus for recognizing the complications. So in 2024, the US government dumbed down. They didn't try to make the coding more sophisticated. They chose to basically eliminate the distinctions being made for this category, along with 3 other seemingly really important ones. They ignore chest pain, severe malnutrition, and even congestive heart failure. So they're in a kind of desperation mode where they've decided they don't like the gameability, and we're going to make the payment formula less precise. And one of the other features of the US is that they don't have any mechanism for updating or changing the payment formula on a regular basis, unlike in Germany and Netherlands, where they tend to update their formulas every year. So that gives them more flexibility about re-estimating the model. It was also convenient with COVID. When there was all this new disease pattern, they could calibrate their model to have a sort of zero-sum payment each year as the total volume of activity changed. So the goal of my project, which has been, I'm the principal investigator, was to update risk adjustment formulas to take advantage of this new information. And we started from scratch, creating categories of disease that were called diagnostic items. And then we organized those items into hierarchies. We have 218 hierarchies, clusters of diagnoses or items that are related to each other. And then within those hierarchies, we wanted to simplify how many parameters, so we clustered the diagnostic items into what we call diagnostic cost groups, which is the origins of the models that Arlene Ashe developed long ago. And we also put effort, as you'll see, into trying to worry about the gameability of the codes that are used for payment. And finally, we tried to imitate the decision process originally used in creating the clinical diseases on the existing Obamacare and Medicare models, so that that would make it transparent to clinicians and policymakers. So just a preview of results so that I can be sure to reach the bottom line. We, of course, improved predictive power a great deal compared to the current model or other models that are used. We created all new hierarchies, and they are trying to be organized the way clinicians think. And you can judge that for yourself as you look at what we've done. We estimate the model on a very large sample of 60 million people. The previous models were calibrated on about 5 million, and we have 3,000 right-hand side variables in our initial model. Despite that large number, because of our sample size, we showed that we don't have an overfitting problem by using estimation and validation sample methods. And then we do the important contribution of this paper today is trying to simplify the parameterization by using this algorithm that improves incentives and reduces the number of parameters by almost 80%. And one of the ways that we've done that also is by excluding some of the diagnostic codes that are a priori judged to be the most vague or gameable and desired not to be in the model. And so, and the final comment that makes me especially proud of all the effort we put into doing this is our models do much better on rare diseases. Is everything okay there? I see some, okay, good. And we made it automated so it will be easy to recalibrate on other kinds of populations and databases. All right, so that's my overview of the introduction. Now let's get into some of the methodology. There's, of course, a very big literature here, and it would take me too long to touch on most of it, but I do think that this is building on lots and lots of prior work on a variety of different areas. And let me jump right to data. We're going to be using insurance data, claims data on a commercial sample of people aged 0 to 64 from what used to be the IBM market scan. In the US, it's known as Meritive. And we are using a 3-year panel of data, and we have a nice 65 million people that we're going to be using. And we set aside 90% random sample for developing the models and 10% of the sample for doing validation. And it's pretty big data, but it's also the same original source as what was used to calibrate the Obamacare risk adjustment model. So the data has credibility to use. And not surprisingly, when you have really big samples, the means on our development and validation samples are essentially identical, less than a fraction of 1% different, and they have both have similar distributions of demographics and diseases as well. And the thing we're going to be focusing on modeling today is on total spending that we've top coded at $250,000. Top coding is a way of making your parameterization and choice of variables less sensitive to having outliers, because spending has such a large upper tail. You don't want that one rare $1 million person to really drive the classification system. Okay, and now a little insert for academics, just saying we estimated everything using SAS, and I recommend SAS for doing these kinds of models because it's excellent at handling very large data sets. We have our development sample, our validation sample is a mere 6.6 million people with 4,000 right-hand side variables, and we can reshape it and recreate it in only 10 minutes on a relatively ordinary computer. And in our estimation sample, it takes 90 minutes. So those are reasonable times. You take a lunch break, you can get it to work. And I also especially like SAS for running linear models. Ultimately, we're rerunning a linear model about 30 times for our machine learning algorithm. And so we can run a regression in 23 seconds. It takes a little longer to reshape the data, but you know, these are very reasonable times. That's a coffee break kind of time. And also the computers that we use for a bulk of our work are ordinary computers. These are not supercomputers with 100 CPUs and many, many terabytes of memory. These are a 64-bit 10, you know, Intel 7 with 7 cores, 48 gigabytes of RAM, and a half a terabyte of solid state drive. That's the secret to success, because most of this is all about the I/O, reading and writing out the data, not about computation. Nonlinear methods, yes, you need huge CPU to efficiently re-estimate things. For this kind of algorithm, it's how quickly can you read in 10 gigabytes of data and do the calculating. And by the way, it's helpful to have 13 terabytes of extra space for your intermediate files. Okay, enough on methodologies, but that should interest you, that you don't have to find a supercomputer to do this kind of estimation. We spent a lot of effort getting clinical input to creating our classification system, this new DXI system. We had 20 physicians reviewing all of the diagnostic codes and cluster them into about 3,000 items. I'll show you some examples in a minute. I made sure the doctors did something that was painful to them. I even had them classify the illegal root codes. In the case of diabetes, you know, diagnoses, they have now 7 characters, and the last 2 characters are the mostly added only in the US system. And the root codes to them are the ones before you get down to that level of precision. The beauty of that is it means our mappings work quite well even on European or other countries' diagnostic information, because we've included the roots that are mostly what are predominant in the WHO ICD-10. Those of you who aren't into diagnostic information, this won't matter. But the reason that I'm excited about that is the model has already been calibrated on Korean and Belgian data, and it had very high performance and relatively few codes not recognized. We aimed to have up to 7 diagnostic items for one diagnosis, and we also created these disease clusters using both information on current year costs, next year's costs, and frequency. And we set a target of having at least 500 people in each of our DXIs. All but 2 of them do have that. And this is an overview I can go through quickly. The ICD-10 system has 23 chapters. I'm going to give you an example of how we created this for injuries, because ordinary non-physicians know what injuries are. And so among all the injuries, we have about 20 hierarchies, clusters of information. There are the ones at the top that are related to what part of your body is injured. And then there are other kinds of things, fractures, minor stuff, which is actually a huge volume of all the sprains and cuts and things. Foreign bodies, even a bullet or a splinter are both foreign bodies, burns of all different levels. And so these hierarchies are useful for grouping together items and then let the computer decide what's the most serious member of that hierarchy. And that's the nature of the algorithm we'll be using. So within each hierarchy, there are these diagnostic items. And in the case of the spine back, we only created 7 of these diagnostic items. These are pretty big, serious ones, as you can imagine. It's hard to injure your spine without it being pretty serious. And then it's interesting, my sponsor, IHRQ, has a team of people that were competing in some sense in creating their own classification system. They have 570 categories. And there was a difference in that they early on decided to include splits based on initial and subsequent and sequela diagnoses. In my mind, that's not a great idea, because that's very gameable. You might say, well, it's not gameable whether it's initial. Well, all it takes is go see a new doctor and suddenly your condition looks like an initial visit, and they're going to code it that way rather than a subsequent encounter. So I think that we're saving that information. That would be something that we're not going to use in the first round. So after we look at, say, diabetes, one that was in the news a lot, you can see we created a relatively large number of initial diagnostic items, and then we broke them down into the 4 major types of diabetes. Type 1, type 2, you can get diabetes from taking certain drugs, or you can get diabetes because a woman is pregnant, for instance, and those are other categories, those are broad categories. And within each one of those categories, you can have any of these main effects. So this is the structure. These are hierarchies, and these are the diagnostic items within the hierarchy. And then, of course, there's a lot of additional information not reflected in this, which side it is, if you have eye problems and all of these things. You might say some of these are direct effects, but we've already coded the coma as being noticed on the diagnosis as a separate main effect. So it doesn't fall only in the diabetes hierarchy. So we're not losing this, we're just putting it into a different hierarchy. Okay, so the physicians worked on these 94,000 codes, because I added about 30,000 more, 20,000 more, and we got this number of main effects, modifiers, and then there's some continuous variables such as your stroke measure or your body mass index. And fundamentally, this project only used the clinical, most precise kinds of measures, these diagnostic main effects. Okay. The first thing we did on a previous publication in JAMA that you can read was we just threw all of those DXIs into an additive model. It was very convenient. So we put the 2,400 right-hand side variables in along with some age, sex variables. And we also wanted to make sure we could always do at least as well as our sponsor, i.e. competitor, with the CCSI. So we also included all of the CCSRs in the models. And in fact, in the work I'm going to be talking about today, we're going to just lump together the DXI ones and the CCSRs and not worry about them. We're just going to call them all diagnostic items. And so when we did our first level additive model, notice nothing about machine learning so far, just additive, then we get an R-square of 56% compared to the existing Obamacare model is about 43%. So that's 13% better, and our sponsor also had an improvement. But they did not worry about incentives. And what I'm going to be talking about for the rest of the day is to sacrifice some predictive power in order to improve on incentives. You can also think of stepwise regression that reduced the number of parameters somewhat. All of this is, by the way, this paper has been accepted. It should appear in a JAMA Health Forum sometime in the next 2 months. And just to validate that there's very little difference between our validation sample that all the results I'm talking about today are validation statistics and the original sample in which we estimated it, because when you have 60 million people, you don't have a lot of overfitting. Okay, so then the physicians conducted 2 clinical reviews now of the diagnostic items. One that I've already described is they clustered items by hierarchy. So that you can think about which diseases are more serious or predicting more expense than others. And then they also went through all of these 2,400 categories and asked the question, would you be willing to pay a plan or a provider more if they code this diagnosis? And they assigned them what I called appropriateness to include scores to all of these. And they were instructed to, for those there's no concern, just give it a 0. And then as you get more and more concerned, you can increase your score to 5. And we warned them that things that were either a 4 or 5, we were likely to exclude from the model to help ground them in something real. And when we were all done, they had coded 52% of the diagnostic items as no real problem. It's a precise diagnosis. I don't worry about that. And then at the other extreme, 12% of them were really considered very gameable. Okay. And by the way, the whole with complications, we considered gameable. We didn't include that explicitly unless there was a specific diagnostic codes that was allowed. But so we had this, and we're going to do sensitivity analysis of where do you want to draw the line. Our base model, we a priori had chosen to lump the 4 and 5s as being outside of use for payment. And then we can look at the sensitivity of our model to using different thresholds. So we worried a lot about incentives, and we wanted to try to make it so that upcoding wasn't automatically rewarded with more money. We also didn't want to reward just putting down lots and lots of diagnoses, so that's why we use clusters of items into DCGs. And we also ended up putting in some screening to avoid negative predictions. Doctors find negative very problematic, although I know as an economist that there are pieces of information that predict you will cost less. And we wanted to make it easy enough to explain to policymakers, at least as easy as the existing one. And we wanted to also be able to estimate it on smaller size samples of, say, 500,000 or 1 million, so that it could be applied in other settings, including Australian states or in larger Medicaid programs in the US. All right, now we get to the heart of our contribution, this new machine learning. I know that some people, that's why they wanted to be here, and some people, this is like, I don't understand what this means, but let's see how well I can do. So I will say most machine learning algorithms, they don't try to estimate them on more than 1 million observations. And that's because they are mostly doing very non-linear, repetitive, iterative calculations. And when you get large N and large K, they tend to grind to a halt, and you can't do that. So, and so we wanted to not throw away the information and try to use this to deal with rare diseases. Another is that many people have multiple conditions, so it's not that useful to only focus on one in predicting their annual spending. Lots of people have 10 or more different diseases. We enforced non-negatively, and we didn't want it to be a black box. A lot of machine learning, where you don't really know why it gets a prediction, it's hard to. And we also made it so efficient that you could re-estimate it very easily from year to year if you wanted to. And so a common framework for this, and it's the one underlying DRGs, is a single regression tree, where you first ask, what is the one disease that best explains the cost of a hospitalization, or in our case, we're using annual spending, and that would be diabetes in our case. And then among people who have diabetes, what's the next most serious thing you might have wrong? And you might say, oh, heart attack. And so then you could go down and you would get to a branch that says diabetes with heart attack. Then there's another group of people who don't have diabetes, and they also have heart attacks. And that highlights the central flaw, I would say, or challenge to using this for risk adjustment, which is that the branch that includes diabetes with heart attack does not get informed by the distribution of spending for the other branches that include heart attack, nor all the other complications of differences in mental illness or skin diseases or allergies or all of these things. So the regression tree is not well suited for using it for annual spending. So this is also true that when you look at what doctors and hospitals code, there's often a lot of overlap. So these are the codes that all correspond to different kinds of heart attacks and heart failures. And you'll notice these three at the top maybe look a little bit more ominous, and that's because they are more specific. I learned by this project that, you know how if you listen to a heartbeat on a stethoscope, it goes lub-dub, lub-dub. Well, you can have a heart attack on the lub part of your heart or on the dub part of your heart. Duh, one's the ventricle and one's the auricle. And so these are different, and they have different strategies. So NSTEMI and STEMI are distinguishing those. Now, they're only going to know that if they've done enough tests. So when you first go in the ambulance and the doctor sees you and says heart attack, they don't know what kind of heart attack you had. So there may be simultaneously an NSTEMI along with heart attack, AMI, along with chronic ischemic heart disease. So you could have all of these coded. And the interesting question is, what do you want to do with all that overlapping information? And this is just one hierarchy, the heart attack hierarchy. So this algorithm, doctors can't really say which one's more serious, so we let the data inform us of how to cluster them. So our initial model is like this. The DCG model specification doesn't look very different, other than that we've grouped them by hierarchy, and within hierarchy, we're looking at clusters, groups of diseases that were called diagnostic cost groups. Okay, so let's go through how our algorithm works. The first part, this area is the same as what it would be with a regression tree, but it's only within one hierarchy, A. And so we would look at the different items, AI, and we would ask which ones put you in the most expensive category for this hierarchy. And so we would group those AIs into a capital AI, a DCG, that corresponds to that highest cost group. And then we would then say, conditional, if you didn't have the most serious thing wrong, we're going to put you in the second highest DCG. And so the hierarchy, when you're all done, you have, in this case, 4 different clusters of diagnostic items. And they have this feature of A1, and then people who don't have A1 but have A2, and people who don't have A1 or A2 but have A3. So they're all orthogonal. Now, actually, that has a nice property. They're very easily precise. There's no hetero, I want the right word here. There's no correlation within these groups, so that you don't have this problem with precision. We will see, though, that problem disappears once you say, but we have more than one hierarchy. So in this case, you could do the same thing and say, well, what's the worst thing you have for the heart attack hierarchy? And what's the worst thing you have for diabetes hierarchy? And this would look very parallel, but we're not done yet, because there are lots of conditions, including heart attacks, where your heart attack is going to take it precedence over circulatory problems of your heart or rhythm problems of your heart. And so one disease might have effects on multiple hierarchies. So that's where we created this opportunity in our machine learning algorithm that some diagnostic items, such as X, might be assigned to the second level in your hierarchy A, but it might also be part of hierarchy B. And if you have X, it ignores that the lower part of that branch for a person as well. So all this is getting at is that we have a multiple hierarchy, overlapping, flexible framework for thinking about diseases' effects on within a hierarchy, as well as other related hierarchies. Okay, and this is a single, we had an earlier version of the paper where it looked like one of these early panels like this one. And then the JAMA didn't like this, so they wanted a single figure summary of our machine learning, and here's the best that we could do. So this is the iteration strategy that we have 2 levels. One is classifying diagnostic items to DCGs, and the other is a series of steps to get rid of negatives, insignificant, and forcing monotonicity, so that you want the coefficient on a higher ranked DCG to be bigger than the coefficient on a lower ranked one, just for face validity. It doesn't actually matter, but it looks nicer when the most serious also has a higher coefficient, okay? So there's also, it's tunable, and you get to choose, of course, the features of the model. How do you want to structure your hierarchies? Are you going to allow negative coefficients? And so the model is very flexible. And then it's also, when creating DCGs, you get to decide how fine they are. Are you going to do a really coarse system with only a few DCGs, or are you going to do a very fine one with lots? So we set a goal of having at least 2,000 people in each of our payment categories, not allowing a difference of more than 30% between the newest group you add to a DCG and the existing mean. We wanted to start by focusing on the really high cost stuff. So we put in this floor for the initial iterations, and we lowered that floor by $10,000. We could have done smaller amounts. And then we also didn't allow negative coefficients in ours. And then we had a pretty tight standard. We would have done even tighter, actually, but the sadly, SAS, the smallest p-value that they will allow is 0.0001. But that's what we ended up using. All of our variables are significant at that level. And our structure allows either for simple hierarchies like this, A over 2 over 3, or two different hierarchies might dominate one member in a lower ranked position, or you can have one condition like heart attacks knocks out a bunch of diseases that are not only in the heart failure category, but also in rhythm and other types. All right, so now I've spent a lot of time motivating this. I've worked on this for 4 years, so I think it's important to know that this hierarchical structure in machine learning could be applied to other hierarchical information. So I put together these two made-up examples. And I have a former student who went to Amazon with a mission of building models that could predict what's the next book you should be recommending to a person. And that's not a trivial thing. It's a really complicated demand modeling. And they are going to use the past history of books you've already bought. So if you go online for Amazon, then you'll see that their homepage gives you this huge list of different categories of books that you could potentially buy. And then I know it's kind of interesting that I look at my last 4 years of book purchases, and I buy a lot of books mostly on Audibles, but I could have bought them on Amazon. So if they were to cross-reference their Audible sales with their Amazon, then I might look like something like this, which is 15 different categories. But that's not the end of the story. If you click on any one of these, I'm going to take children's books. I have 2 grandchildren now. Then what you'll find is the children's books itself has all of these categories. And notice that that includes biographies and cookbooks and geography. Children's cookbooks is a category. So you can imagine all of these pieces of information. Are you going to create a biography I buy for my child equally with a biography I bought for myself, an adult book? So it's not an easy thing, and I would want to let the model, the computer, have some algorithm over various hierarchies of maybe children's books or of biographies to figure out how to put this information together, maybe not in a linear model, but in a framework to use. And by the way, you also have these other hierarchies of the age structure and the type of book and how current do you want to be. It's not a simple choice at all. And of course, now you say, oh, we'll just throw it in machine learning. I'm sorry, there's thousands and thousands of books and 1,000 different permutations of these. Even machine learning algorithms are going to have to simplify it in some way. Okay, and by the way, this offers tens of thousands of those. So these are all different challenges. So that my other one is related to a different project I'm working on where we're trying to understand systemic bias in economics departments. And the key thing is there's a lot of different ways you can organize geographic and origin information. For instance, you could go by country of origin, or you could organize it by language. Now, these two are kind of distinct, but not the same. Is it that you like practicing with other people who speak Spanish, you're co-authoring, or is it that you like people from Spain? Those are different definitions. Or ethnicity. There are many countries with more than one ethnicity. So these are heavily overlapping, and I can see that maybe a machine learning algorithm like we have might help. Then there's even gender, which might seem like a binary flag, but then there's all the people who are other or the people who prefer not to say, which is an even larger group of people. And then you also have different ways of inferring gender. So these are interesting points that I can imagine a hierarchical structure to try and simplify this problem. Back to our model, because I have only 17 minutes left. We start out with a linear model, and this is what we're going to be trying to estimate for DCGs. And I think the easiest way of seeing this is for me to show you some silly results. The first thing is when you have 2,000 right-hand side variables, looking at long lists of coefficients is not the way to go because it's not informative. But one thing we did do is we created informative labels for all of our hierarchies and all of our DXIs so that they're easy to work with for other purposes. So these are the ones in the heart range, and these are the ones in heart failure. And one thing I like about this to point out is because we start out with 60 million people, we have a lot of people in each of our categories, which gives us incredible precision of our coefficients. In addition, we made them orthogonal, so there's no multicollinearity across them. So these are the coefficients, and notice the confidence intervals. You would all die to have a confidence interval of plus or minus 2%. Okay, so now because they're painful to look at that way, we find it useful to look at charts. And one thing you can do is you run a regression, you can order the coefficients from the highest to the lowest, and then it helps you figure out what's the worst kind of nutritional metabolism you can have. Well, those minerals like potassium and such, those are really bad, and those can cost a lot to take care of. So this is what the hierarchy looks like with the DXI model. Notice the DXI in bold up here for these nutritional. What our algorithm does is it replaces that detailed function with a step function, where initially the highest category ones get classified into one, and then there's a second DCG, and then there's a third one that has a lot of DXIs in it, and then the lowest one is barely a positive number, but there's high n, so it's still determined. So fundamentally, that's what our algorithm is trying to do, and in the process, we wanted to get rid, we could have left all of the diagnostic items alone, and we wouldn't have reduced parameters, but we reduced from 39 to 7, so that's where we're getting the 80% reduction. And when we talk about the diabetes example at the beginning of this talk, we started out with actually 83 of these because of the interactions with the different types of diabetes, but a large number of diagnostic items. And these were ordered into, well, these are all the endocrine. This is misleading. So actually, among the diabetes ones, I think the number is 12. And we had 4 hierarchies, and there were lower versions of each of them. But interestingly, after we had run our sorting algorithm, we simplified it to only 5 of those mattered and only 4 coefficients, only 4 categories. So the answer to the Obamacare is they should definitely split out type 1, type 2 diabetes and the drug-induced diabetes and other. Those are meaningfully different from each other. And those are kind of not very gameable, you know. All right, on the big picture, when we do our machine learning algorithm, here's the existing CMS model that the Medicare and Obamacare is the right word to use. It's the HHS HCC. I've been trying to minimize my use of acronyms. So this is the Obamacare model. It has 166 variables, including 30 of them are age, sex, and a bunch of them are constrained to be the same. So that's where we start. And then this is our friendly AHRQ model with 567, including the 30 age sex terms. We start out with 2,366 after dropping the gameable DXIs. And then as we iterate through, we first assign only 1 DCG, and then we assign, I don't know why that has only 1 more, but we remember we're dropping DXIs as we go. So actually, there's more than 1 DCG. It's just that we drop the DXIs as we put things into DCGs. And so as we go along, we shrink the number of variables on the right-hand side, but we still reach the end where we can't find any more to cluster. And then in one bold step, we take all those remaining insignificant or negative coefficients, we drop them, and we get rid of 600 more variables, roughly. And then these last little steps are where we force statistical significance and drop the negatives, and we end up with 624 parameters. So that's where we get our 80% reduction. And this is what the implications are in R square world. You start out with the existing model, 42%, our competitor, 54%. We do a little bit better, but we are worrying about incentives, whereas theirs is just including all kinds of junk. So there is a difference that they didn't drop the discretionary diagnosis the way we did. So we go along, and you can see that we can improve incentives and drop 80% of the coefficients with barely a change in the R square measure. Lots of controversy about R square. It's not the only model measure one should use, but it's convenient. And this is just one more example saying in the case of the diabetes hierarchies, we started out with our initial sets of DXI categories, and then eventually some of them get assigned to DCGs, and then the DCGs, they're actually pretty stable even as we're adding and constraining lots of other coefficients. And this one, the lowest cost one, turns out not to be statistically significant and gets dropped by the computer in the last 3 iterations. Okay, so the gains from doing all this is that we end up with improving incentives, and we've imposed hierarchies that ignore the less serious conditions, and we've immediately ignored the conditions that are more gameable. This is my favorite figure. If you can remember, one reason to have done all this hard work is this figure, okay? This is a graph in which each of these broad sets of bars is a category of people, and that they're grouped according to how rare is the rarest diagnosis they have. So the people in the top have at least one diagnosis as rare as 1 in a million. And the people in the bottom don't have any diagnoses. That's one of the more common things. And then above that is a group having things like hypertension or low-cost minor injuries. So these are, the key thing that is aha moment is to realize that 16% of the people have a condition that's more rare than 1 in 100,000. That's 1 in 10, 1 in 10 in a million. Or if you want to, going up to 100 per million, that's 1 in 10,000. If you see a doctor with a disease that's 1 in 10,000, they probably are only going to be treating about 1,000 patients, distinct patients that year. That means they will only see somebody with your diagnosis about once in every 10 years. It's easy for them to say, I don't know what to do. I don't want to spend lots of time studying in the library of what to do about your rare disease. And this is a group vulnerable to under-treatment. Now, the existing HCC model is the second model down here. They are underpaying for those people with rare diseases by around $7,000. And at the other extreme are wonderful, let's go down here. The people with no diagnosis are being overpaid. The plans are making money on them under the existing health formula on the order of about $2,000. But as you look at the bottom three, all of the ones, including CCSR, does quite well down here, but our models do the best. The DXI additive almost has a 0 error, even to the less than 1 in a million. But the DCG models also look very strong about not mispricing these people with rare diseases. So I think that this is a new way of thinking about this problem. And this is common with simplified models. Machine learning has the same problem when they're trying to guess your name. You know, they're using facial recognition. Those models do very badly on certain ethnic minorities because the models haven't been trained on people. So models trained on US data don't do well on people from, say, Africa or people from China because there aren't enough of them in their initial development samples. And conversely, models developed on Chinese populations are going to do poorly on Caucasian samples. So this is just pointing out that large sample sizes and fineness of your classification system can improve your performance in these different kinds of rare diseases. And then this is the footnote to that. It's a reminder. I didn't even comment. I noticed a paper just presented this week was using the Charlson Chronic Index, CCI. It has 18,000 citations just in last year. It's a very widely used measure, and it's a terrible measure because it only reflects 18 chronic conditions. And so it's an example of something that's used because it's easy and free. Our software is free already that does the DXIs. We are eventually going to post the DCG algorithm software, but you will be able to use this for your own research, and it will do very well. There's sensitivity analysis. We have our base model that I've been talking about, and we, on average, do very well, even for people who have a disease that's as rare as 100 per million, which is a 1 in 10,000 rate. And I've already talked about some of this information. These are competing alternative structures of information. If we just use the additive model, we could gain about another 5%, but that wouldn't worry about incentives. And another thing we can do is, because we parameterize this degree of discretion, you can then rerun the model using different thresholds. The one we chose in the middle here is without forcing, is being less than 4 or less, or less than 4. And that was our 0.53, but you can also, you could become even more stringent and try and get rid of everything that has any concern. That would still use half of the diagnoses, and you would sacrifice another 6% of your R square, or 5%. And the other thing is that somebody could go back and redo the assignment of ATIs, and I would be perfectly fine with that, because we had clinicians do it, and maybe policymakers or even economists might have different judgments. And I would love to work on empirical measures of what's gameable or not. Okay, and so that leads us to, we also do lots and lots of other variations. And the bottom line is that our models do about as well as any of them once you worry about incentives. So we could have thrown back in these things like factors influencing your health. Those are very gameable and vague. Or we could have thrown in external factors like, were you driving a car? Where were you injured? Those are also kind of not well coded and gameable. We're committed to making things public. This link is in our 2022 JAMA paper about the DXI system, and we will be updating the software that is in there. And so I think that brings me to my conclusions and ideas for future work. I didn't ask whether I can go up to the end of the hour, but I'm going to. So basically, we don't currently use any of the pharmacy information, and we haven't used the modifiers in the current paper. There's lots of other work could be done on other outcomes and different populations. I'm hoping to get grant support for doing Medicaid and Medicare models in the US. I'm also eager to work with people in other countries who have good data to apply these techniques. And we have a relatively large number of parameters that will make it hard to estimate on samples of, say, 500,000 or 1 million. But by making it down to, I know 600 seems like a large number, but because they're orthogonal, the right thing is this about 200 different hierarchies, and it's choosing a structure within them. So I'm hopeful that we'll be able to estimate in Massachusetts with samples of about 1 million. That's my current goal. And if not, you can put in a single risk score based on a US calibrated model. And when I did that 20 years ago using Australian data, the answer was that the US based model gave an R square in a concurrent framework that was only about 5 percentage points lower than the fully recalibrated model using all the different styles of care in Australia. In other words, you can do quite well even using a model calibrated on a different country. All right, and so we have a readily interpretable, predictive, avoiding negative predictions, somewhat resistant to upcoding, and dropping vague. These are all additional things that you could do, and I think there are lots of interesting projects. I'm not going to have time to go over them. So I think that, as you think about how you would want to revise them in the settings that you're interested in, that's a good question to be asking. And that is my last slide with 3 minutes left. So I think we actually have about 5 for questions and answers.
Thank you, Randy, for a wonderful presentation. So we have quite a few people online. Josefa is probably going to
just want to see if
check whether there are some questions, but in any case, guys online, please.
Denzel Spybig, I see you have your hand up. Why don't you just speak up?
Yes. Or write your question if you're not allowed.
Well,
Denzel.
if you have a microphone, that is preferred. Yes. Oh, you may need to unmute him.
That's the thing. Yeah.
So you should say your computer.
So you should be able probably from here.
From the participants.
Yeah.
Yeah.
No.
You have to go way down with this. There it is.
Denzel.
Oh, this is the one with the
Yeah,
hands?
Allowed to talk.
All right.
Denzel.
Try now.
Hi, can you hear me?
Yes, we can.
Randy, how are you?
I'm very good. We'll say hi afterwards, but yes.
Look, I think I saw it flash by on your work, future work, but it seems strange to me that you didn't incorporate any of the information in the panel. So you made the point that you have a panel with 4 years of data, but as far as I could see, the panel nature of the data wasn't exploited. And that seemed to be a strange initial choice for what you're doing. Having said that, I think this is fabulous. This is one of these times where even in the machine learning world, it's not all about letting the data speak, right? It's a combination of clinical information and letting the data speak.
Yes, in the thesis chapter that Corinne Angiola, who by the way is the lead programmer and superstar that made this all possible, she does a cluster correction for, you know, the fact that we have repeated observations on each person. It's 3 years panel, and the basic feature of health spending is the correlation from year to year is only around 10%, and therefore the bias that is what you worry about from ignoring the clustering is not that great. But yes, one can use the panel, but we're not trying to use multiple years of information to do the prediction. That would be the real benefit. Okay, I'm not in charge, but somebody else is going to choose someone else.
No, I mean, anyone else who wants to ask questions, maybe here in the room?
That seems like a pretty stupid question, but why is your sample size ages 0 to 64?
The answer is because that's the data we had, and the Obamacare model only applies for people under age 65. There's a separate formula for people over 65. Yeah.
I might have missed it, but did you look at whether people were insured or not? I know that's
This is a sample only of people with insurance. And so there is a problem that people who don't have insurance, it's almost impossible to get all of their detailed medical records because it's sprinkled around and maybe self-paid, so it doesn't go to any insurer. That's clearly an issue of importance. Most people who are uninsured are actually then insured by the Medicaid program. And that's a group that we're modeling separately.
Good. Any other hands up? I don't see anything here. You see hands? No.
Well, and a chance for anyone else to ask a question
Yeah, just put your hands up.
or speak up. I've unmuted everybody or enabled it.
Now we have to do it one by one.
Oh, I
So
see.
just put your hand up if you have a question.
I do have a question
Or
about
chat.
the initial stages of how these diagnoses are like clustered by physicians that I've kind of always had. So are they looking at like a really long list basically of ICD-10 codes and then saying, okay, yeah, this and we'll go here, and you know they have to do that for each one of them, or?
If you go to the 2022 paper in an appendix supplement, you can see the 3,000 pages of figures that we held in front of physicians. Each chapter has a number like, let's say, 100 pages of these detailed bar charts, because the efficient way of clustering is looking at bar charts where you're saying, okay, the diagnostic numbering system tells you a lot of information about what's similar. But then within each diagnostic code, it may be that all of the 0.01s belong together and you have to have a skipping pattern across different diseases. And that's the advantage of humans doing it instead of just leaving it up to a computer. But yes, they looked at thousands of pages of bar charts, and it was automated creating them, but we brought them in. We would spend 2 hours at a time trying to go through a number like 100 of these bar chart pages and forming clusters with good recording done by non-physicians. Yep. It did cost us about $200,000 of our budget, because we did pay the doctors. It's just, there's a limit to how much you can pay when they're at their rates. Yes?
just on that, did you have the opportunity to compare what, say, the algorithm would group on its own in terms of those groups without the doctor's input to compare the two?
Not on exactly the same data. I did encourage my RAs to try other like lasso estimation or other things, but the problem is that the first cut of how you want to cluster them. I also have a colleague at BU who's done work on fraud detection. We're using machine learning to just use clusters of the numeric diagnoses and let the computer find those. That's a little bit easier because they're kind of like a continuum and you can try different break points. But certainly there are other ways to do it, but I think we end up with a nice clinical coherence. And if you want, you again, look at our hierarchies online and our codes, and you'll see that it's easy to relate them to things physicians can talk about. Yeah.
Wonderful. Great. Thank you, Randy.
Okay, good.
And for those online, of course, thanks for coming today with us. And obviously, this will go online for those who will connect later. Of course, interact with us. We will have another seminar in a few weeks. Thanks. Goodbye. Stop the recording.